let's meet today's speakers. Today I'm joined by Jeff Williams and Ellen Williams. And I will then hand over the stage to Ellen and Jeff.
Great. Well, thank you all so much. I will start sharing my screen and just let you know that we are thrilled to be here and talking to this community of Volta Foundation Battery Network. And at Exum, our mission is to redefine how we measure the world around us. And we have done that with an analytical instrument that we're pleased to talk to you about today. And if I can figure out how to launch the polls, then I would love to hear from the audience how you all are currently using analytical techniques. So let's see, I think I successfully launched the poll. Is that true? Michael or Jeff, can you guys see the poll? Cool. Yeah, I'm starting to see some
Looks like
results.
you did.
Awesome. Yeah. So, we've listed a few ways that, we know that our customers use our tool and would be really interested to hear from you all how how any analytical techniques are currently supporting your work. So it seems like a lot of compositional analysis, some people on a lot on the failure and defect analysis. That's great. We'll certainly be talking about that, development of new materials. Great. Okay. Well, that is very, very helpful to see. The other thing that I have to say in the intro is Jeff and I are not related. So we just happen to have the same common last name. And I am, pleased I will be handing it off to Jeff here shortly to give us an overview of the technology, because as our CEO and CTO and founder, he's really the driver behind this new technology that was really developed to make mass spectrometry easier to use for solid and powdered materials. So for today's agenda, we will start by just setting the stage with how this technique fits into some of the landscape of traditional instruments, then go through the fundamentals of this LALI TOF-MS technique that is included in our Massbox instrument. Some of you who may be familiar with Exum or maybe have seen this technology before may notice that this box looks a little bit different, the geometry of it. And that's because we have created a new version, a next generation of the system. And so Jeff is going to walk through those recent advancements with you, and then he will hand it back to me to go through some of the application examples. And so let's see. I'll share the results of our last poll, because what I want to do is look at the other poll. There we go. So I will launch the next poll so that I can hear from all of you which of these application examples are most relevant to you, to your work. As you've heard, the title of this is From Ore to Anode. There are applications for this technique across the entire battery life cycle. And so we will be going through some of the geologic and mineralogic examples on let's get the critical battery elements out of the ground and process them, all the way through to the developing a new cell chemistry and analyzing cell components once we've already assembled the cell. So it looks like most people are on kind of the anode side of things, but we do have some folks on the ore and mineralogy side of things. So that's great to see. All right. Well, with that, Jeff, I will hand it off to you to go through this section.
Perfect. Thanks, Ellen. And yeah, thank you guys for everyone for being on the call today. So really excited to be here, and figured I would start with maybe just putting the Massbox, in two dimensions of how we could think about where we fit into the market in general, and how you can start to think about how to use it. So on the y-axis here, we have a detection limit, right? So how low of a concentration can you analyze? So this is going from weight percent at the very high level, all the way down to parts per billion. And then on the x-axis, we have resolution. So meaning if you were to make an image, a chemical image of something, or a visible image of something, what's the smallest feature that you could expect to see? And so, kind of in the top left-hand quarter here, a lot of people on this call are probably familiar with SEM-EDS, where you're using an electron beam, and you can see really small features, right, down to nanometer level, and usually under, a few tens of microns of area that you're assessing at a time with traditional instruments. And you're only able to really see weight percent level things. So major element chemistries most of the time, and so a large limitation on not just what concentration you could see, but also what elements you can see, right? There's a lot of elements that just are never going to show up with the SEM-EDS system, but still a really incredible tool for imaging, especially like on that scale. On the other side of the equation, we have ICP-MS, right? So very, very good detection limits down to parts per trillion in some cases and parts per billion level detection limits. Still some limitations on what elements you can see, but you are taking that sample and you're digesting an acid, right? So I put this kind of on the resolution of millimeters to centimeters because you're taking some amount of material, digesting it, and you're getting one data point out of it. And you can see there's kind of this gap, and there's obviously a lot of other tools we could talk about here, but I just think that this frames it super nicely. But there's a gap in the marketplace of, I want to look at something that's 3 inches by 3 inches, let's say, kind of larger scale, but I still want to be able to see fine features, and I need the power that ICP gives me with detection limits. And that's where the Massbox fits in here inside of this. We can look at things on the 5 micron scale, smallest feature, and we'll talk more about that later, or we can adjust that spot size from 5 microns to 150 microns. We can analyze an area of 90 millimeters by 90 millimeters. Anything you can put inside that area, we can map the whole thing, still at that 5 micron scale if you wanted to. And at every single pixel, you can get the entire periodic table down to parts per billion level sensitivities. And we'll show you some examples of that. So it's one box, as you can see here, one power cord out the back, no consumables, load anything into our sample holders that we'll talk about in a bit, put it into the machine, and you have this capability of doing chemical imaging at high resolution with large sample sizes with still high limits of detection or low limits of detection. So let's talk about kind of just some first principles of how it works. So this is a laser-based technology. So some of you may be familiar with other laser-based technologies, and we do things a little bit differently here. We still do what's called laser ablation. So this is LALI, TOF-MS. I'm going to break down that acronym there. So laser ablation happens. This is ultra fast ablation. So picosecond laser. We don't have to go into the details of that. Happy to answer questions about it later. But really, we want to optimize for a neutral particle cloud being liberated from the sample surface that's stoichiometrically representative of the solid that we ablated from. And we don't want plasma and we don't want particles or molecules. We want to optimize for neutral atoms. So we have a special laser system that we tune just for this to happen. And this all happens inside a vacuum, right? So this is great for obviously everybody on the call in the anode space or cathode, where you want to have air-free transfer. You don't want to expose this to oxygen. And we have the ability, and we'll talk about this later, to take it from a glove box, put it into our system, fully air-free, and it goes into a high vacuum environment so you can analyze it natively. And very minimal sample prep. We just need solid and flat, and we'll go into more details. So once we have this neutral particle cloud, the next step that we have to do for our mass spec is we have to ionize it somehow. So instead of sending those particles and atoms through a tube to another plasma, what we do is we take another laser and we come across and we ionize that neutral particle cloud. So we basically put such a high density of photons in there that it excites an electron one time, then excites it again. And now it's so far away from the nucleus that now we have an electron and an ion pair. And then we can push those electrons into a time-of-flight mass spectrometer. So we can ionize basically every element on the periodic table. And then every laser shot, we kick it into what's called a time-of-flight mass spectrometer. So time-of-flight mass specs basically work like kicking a soccer ball or kicking a bowling ball with the same energy. The soccer ball is going to go a lot faster, right? And so that's what happens with lithium versus uranium. Lithium's going to fly very fast down our tube, and uranium's going to go fly very slow. So if we have one detector and we're just sitting there and waiting for the ions to impact, we're going to see lithium, then we're going to wait a little longer, we're going to see carbon, then silica, so on and so forth, all the way out to uranium. And because it's in vacuum, and because it's a mass spectrometer, so we're literally measuring the ions that we are liberating from the sample surface, or the atoms, to the detector, we're going to know exactly for sure that it is that element, because we can get a very clean mass spectrum with isotopically correct signature to say, yep, that is definitely lithium, it's definitely chromium, iron, so on and so forth. And our software is going to handle all of that for you, of the identification of those elements. And we don't have to worry about a lot of interferences like you might have in spectral or even other mass spec spectra. It's very clean, isotopically correct, with every single element showing up at every laser shot. And so what this enables us to do is, with this technique, we can do kind of three major modalities. The first one is quantitative workflow for most of the periodic table. So we like to say lithium to uranium, and we ignore the noble gases, right? We don't do those, but we do every other elements. And critically, we do those light elements that are very difficult to do by other techniques. So that kind of top bar of the periodic table there. So we're very sensitive to lithium, and we for a lot of the metal space, especially, but also relevant in batteries, we do a lot of carbon, nitrogen, oxygen work as well. And that's at every single laser shot that you get. So every pixel, right? And now we're going to move that sample in space. When we do that, we can create a chemical image. So that's our second modality, is we do quantitative compositional analysis down to low parts per billion level. And at every pixel, then we can see where is that chemistry happening. And what you're looking at here, this is a map of a thin section that we've done that took about 20 hours to do by another technique. We did this map in 20 minutes. And at every pixel, we have the entire periodic table, even down to the low levels of yttrium inside of this one mineral grain that you're looking at there. So this just starts to have you think about how you could use this, not just for, can I get my compositional analysis, but can I see where my chemistry is? Where's my lithium plating out? How's my SEI layer forming? All of these sorts of questions we're going to get into later. So now you might be thinking, well, you're removing a little bit of material. That's about tens to hundreds of nanometers per laser shot, and you're analyzing it. What happens if we just keep repeating it? Well, what we can do is go back over that raster area, that's what we call it, and we can then create a 3D profile and look in 3 dimensions and map out, what does that look like as we go down? Is it homogeneous? Is my lithium distributed how I expect it to be? Am I getting layer or contaminants that are piling up in certain areas? And so Ellen's going to walk you through an application where we looked at that, where we went all the way through an anode to be able to better understand the chemistry for a customer. So all of this we have developed into one platform, and what I'm really excited to be rolling out about for the past few months now, and we already have them coming off the manufacturing line, is our next generation system. So as Ellen mentioned, this box here, if you've seen the Massbox before, looks a little bit different. We took that past 4 years of learning. We took all of that and we said, what would be the ultimate expression of this technology? And we put it into this case. So this is harder, better, faster, stronger, and kind of every metric that you can think of when it comes to this. But most importantly, it's built for industry. So high uptime requirements, robustness, reliability, but also being able to stand up to the high throughputs. And how do we do that? Well, we created an entire API so that we can work into automated workflows, which happy to answer a lot of questions on that. But this allows us to do thousands of samples per day. So some key advancements maybe to help you think about what we really changed here. We changed how we hold the samples. So we created an entirely new sample introduction system. This cartridge here is just one of many cartridges that we offer, but everything gets loaded up to a top plane there. So there is no more height adjustability required. We can take all shapes and sizes, and everything just gets pushed up to one plane. What you're looking at here is holding a bunch of gemstones that are held into a wax. But this is just because I wanted to highlight we can analyze anything that's difficult to hold. And we also have a whole mechanical workflow that we do with customers where they will tell us what sample sizes they expect to have. So 13 millimeter pucks, 1.5 inch pucks, some thick sections, some cores, some battery slices, whatever it might be. We can customize anything within this volume to be able to load into our sample introduction system. Makes it really easy, really robust and reliable, and obviously lends itself really well to robotic arm handling for automated workflow environments for high throughput. The next major thing is we changed over to what an airlock system. So instead of venting an entire chamber, loading it up and waiting about 10 minutes, we are now pumped down, ready to analyze in under a minute. So again, for this high throughput automation sequence where it can be controlled by a, let's say, computer vision system that's automatically telling it where to analyze, or just by hand choosing where you want to analyze, press go, you're ready to go into a minute. So way faster pump down for higher throughput. And one of the major improvements we did for the analytical side is we improved our detection limits by an order of magnitude. So when I say, getting into the low parts per billion level, this is 300 ppb lead that was from a certified reference material. And you can see that we're seeing all the three major isotopes of lead, plus a little bit of the fourth, maybe if you squint your eyes, but really importantly, seeing those three major isotopes well above the background signal there, getting down to parts per billion limits of detection. So this was huge for us going into, especially into this space, on the core side as well, when we're looking for sometimes things in the hundreds of ppb can be an economical resource, but also in the anode side as well, when you're looking for low limits of contamination, let's say, or quality control testing. This was a huge improvement and gave a lot more robustness to our quantification as well. There's a lot of other stuff that we did within this version that happy to answer more questions on, but the key takeaway is it's easier to use, it's more robust, better limits of detection, and it pumps down way faster, and it's built for industry. So all of that gets basically packaged up into what was a large focus for me, which was our interface. I wanted to change the way people experienced a mass spectrometer. I wanted to have this easy environment where you're basically being walked through a workflow or setting up automated workflows that anybody could learn to use in half a day of training, and they're ready to go on their own. From everything from method developing to quantifying samples, it's all easy to do. So I'm just going to play this video and I'll kind of talk through a high level. So the first thing we're going to do is we're going to open the sample door. This is that airlock lid that I talked about. You're going to then load in your samples, tell it what kind of stage is in there. There's then a scanner that comes across the sample that scans a macro image of the system. If we're happy with that, that's what we use to macro navigate. We can then zoom in and transition to a microscope view later on, but this really helps us to look at where we're going. We then select the type of sample holder, and each of these areas that you're looking at here, this is where your data is saved, and that's how you're going to interact throughout the entire process. So this, for example, is a clay that actually is a lithium-bearing clay, so relevant to this conversation. We know, kind of some of the composition of it. We're going to label all of these samples. You can see that they show up there now in the software. And then the next thing that we're going to want to do is we're going to want to start putting down some rasters or some spots or where we want to analyze. So we're putting down a raster here. We're going to make this a 20 micron pixel. We're going to do a 3 millimeter by 1 millimeter spot. We're going to do this 3 times, let's say, just to get 3 replicates of this. Now, I don't want to go do this for every single sample. I can move it around, and then I can copy it and just paste it over to every sample. You can also, there's a selection tool where if you have a lot of different features you want to do, you can just select, copy them over, super easy to set up your runs. So within a few seconds, you basically have everything selected here, and we can go back now and add another feature, which is a spot. We're going to do a 2-minute dwell on the spot, and we're going to move that to the very front of the queue just by dragging it up. We want to do the spot first, then go do our rasters. By this time, everything's already ready for analysis, so we're just going to press start. And then now what's happening is the stage is now moving, it's doing our raster, and we are starting to inspect our mass spectra, make sure everything is as we expect it to be. That's 10 isotopes, for example. Now we're looking all the way over at lithium. So the very first one, and what you see all the way out to the right, was lead and lithium being shown in the same mass spectrum as we are moving around on the sample surface. And what's happening automatically as well is if you notice on the periodic table that's being shown there, you're seeing some squares being shown around it. We are identifying what's happening and what elements are in the sample while you're viewing it, and you can click on those elements and it'll start viewing it in time as well. Obviously, this will go into a lot more detail on the processing side, which is the next screen or the next stage of the analysis. But that's how easy it is to put your sample in, choose where you want to analyze, press go, and let us be the analytical chemists for you. So that's just brief overview, just to kind of orient you to the Massbox in general. I wanted to then hand it over to Ellen and probably more what everybody here wants to talk about today, which is the application side. So, Ellen, I'm excited to have you jump into some mineralogy first.
Yeah, thanks so much, Jeff. Yeah, so hopefully you got to see how easy it is to set up the analysis and how versatile these analyses are. You can do a spot if you just want to dwell into the material and determine what it is. You can do these raster areas if you're trying to get a bulk composition of a heterogeneous material, or these raster areas can actually turn into elemental maps, which is what we're going to look at in our first application example. So as you saw in the agenda, and as I know some of you are interested in these kind of ore and mineralogy application examples, we'll go through a couple on this side of things. So the first one will be, how is this elemental mapping valuable for mineralogic samples? And so what you're looking at here is a rock thin section that was analyzed with another technique that analyzed half of the thin section and determined some of the major mineralogies that are included in this thin section. So you see arsenopyrite, chlorite, ilmenite, and then our technique analyzed the other half of the thin section, and we created these elemental maps. So a typical workflow for LALI TOF-MS is to analyze these broad scale, millimeter scale elemental maps with a relatively large spot size. You can see that we chose an 80 micron spot size in this case that allowed us to acquire this analytical area in about 41 minutes. If you may have noticed when in Jeff's video that he showed of the user setting up an analysis, the software always tells you how long the analysis will take. And it's always a trade-off. We can do higher resolution. It's going to take longer. The laser fires at 20 hertz. And so essentially it's just a trade-off between how many laser spots am I going to do? Am I going to do a large area or a smaller spot size that's just going to take longer? And then when we look at these elemental maps, each one is on its own relative scale where we see these reds, these oranges, those are relatively high amounts of a given element. So for example, you can see on the iron map, there are distinct areas with relatively high iron. And then on the titanium map, we see areas where titanium is relatively high that correspond with other areas of the sample. So titanium being a major component of the ilmenite, and then iron giving us other mineralogic cues. But in particular, what this study was focused on was cobalt. And we all know in this audience the value of cobalt, especially with its prevalence in the NMC cathode, that determining where the cobalt is and what minerals are hosting it was of particular interest. So you can see how we have identified this area with relatively high amounts of cobalt, and then we can do a secondary map which is smaller, covers that smaller area of interest that we want to see with a higher resolution. In this case, 20 micron laser spot size. This did take a bit longer, so an hour and 40 minutes, but you can see a much higher resolution picture of how that cobalt is distributed. And just a reminder, each one of these pixels that you see on this elemental map is one of those 20 micron laser spots and has that full mass spec of data behind it because all of those elements show up in the time-of-flight mass analyzer. So clearly there are some areas of this sample with relatively high amounts of cobalt. And then we can take a look at some of the other elements like the iron and identify that, there's relatively low amounts of iron where there's high amounts of cobalt. We can also see how the titanium is distributed. We see that there's relatively low amounts of manganese. So all of these major elements help us understand, what mineralogy is hosting this cobalt, which is the element of interest here. But where this technique really adds value compared to some of the other techniques is with something like zinc. So zinc is a trace element. You can see that, the picture is relatively blue, it's a relatively low concentration of zinc everywhere on the sample. Zinc is in the parts per million level. So likely might have been below the detection limits of other techniques that might have been used to look at just the bulk elements and determine the mineralogy. But Massbox, being a mass spectrometer, can pick those trace elements up. And in many cases, this can be very helpful to better understand and characterize the mineralogy and its formation history, to better inform how are we going to extract this element of interest, and then how are we going to process it once we get it out. So this just demonstrates how this can be very complementary to some of these other techniques that can do automated mineralogy, but maybe lack the sensitivity to identify some of these trace elements. The other key piece that Jeff hit on is this technique does not require any sort of argon gas or special facility requirements. This can actually be brought to a field office. So these types of high resolution elemental maps across maybe a core that has been directly pulled out of the ground, that can be analyzed in a field office without having to send this back to a centralized lab to get a high resolution, microprobe or electron microscopy done on a sample like this. So again, very complementary to some of the existing techniques and providing some additional value on trace elements, as well as bringing these capabilities to a field office. So now the next example that we'll go through is another key complementary capability is being able to reliably quantify lithium. So we know that X-ray techniques can struggle with some of these low mass elements like lithium, but of course lithium is very critical to the battery life cycle and understanding where lithium is in mineralogic and geologic samples. So what we're looking at here is a set of reference materials that are all different mineralogies. These are included in what's called the lithium exploration set that is created by a company called My Standards. And these reference materials are all different mineralogies, different blended sediments, but they have a known amount of lithium in them. If you're not familiar with these types of solid reference materials, they go through a very rigorous process of various techniques and different analytical labs, all converging on an agreed upon value for lithium as well as other elements in them that are then presented as a certified value. So we have these reference materials that we can analyze in the same analytical session. And then we have the measured intensity of the lithium signal with our technique. And we plot that against the known concentration on the x-axis here. And this is how we create a calibration curve. So we see that across these different lithium standards that we have here, we've got lithium, everything from 12 parts per million in one sample, all the way up to 2.6 weight percent in another reference material. And we see this nice linear response from our detector that gives us confidence that if we were to analyze an unknown rock or mineral sample with some amount of lithium from 12 parts per million to 2.5 weight percent, we could plot it on this curve and determine how much lithium is in that sample. So this just shows you, how this technique, how we get quantitative data out of the mass spec that we acquire on an unknown sample. And it gives you a sense of how we approach, analyzing an unknown material. Having multiple points along a calibration curve is ideal when we have some sort of unknown material and an unknown amount of lithium that could span multiple orders of magnitude. But I will say, we don't always need 8 reference materials in order to get quantitative data. We can do single point calibrations as well. So if you know the type of mineralogy that you've got and you have an unknown with that same mineralogy, it can be very straightforward to just use a single matrix match reference material and do a single point calibration. But of course, we know that that's just not always the case when it comes to exploration. We may have no idea what rock type we're in, and so having a calibration curve like this allows us to span a wide concentration. So those were the 2 application examples that I had on the ore side of things. And just to quickly summarize of how LALI TOF-MS has those key advantages and really those complementary advantages to the traditional techniques that support the exploration, how we're going to extract minerals, as well as how we're going to process them. the ability to do quantification, everything from parts per million all the way up to weight percent, especially those low mass elements like lithium that are challenging with X-ray techniques, carbon, nitrogen, and oxygen that can be challenging with other spectroscopy techniques. Those can all be done with this technique as well as at least one reference material. You saw how we can do those broad scale elemental maps with micron level resolution that give us an understanding of how those critical elements are distributed and what the mineralogy might be for hosting them. And then you heard from Jeff about this open format stage that allows us to analyze any number of samples within that 90 millimeter by 90 millimeter area that could allow us to do a very high throughput analyses of multiple small grains or powdered samples, or potentially, large core samples as well fit within that area. And then, as I mentioned, this can be a field deployable system. You can actually bring this benchtop instrument, plug it into a typical power cable. All you need is basic room temperature control, so it is suitable for a field office. And with that, I know that the majority of this audience is interested in the application examples on the anode side of things. So I'll now walk through 3 application examples on anodes. And I do also want to point out that, we happen to have a lot of application examples on anodes. It seems that a lot of people are still just, studying and characterizing anodes more so than cathodes. But again, any solid material can be analyzed with this technique. So we can analyze cathodes, we can analyze separators, solid state electrolytes as well. Anything solid can be analyzed with this technique. We just happen to have a lot of application examples and a lot of customers that are doing work on the anode specifically. So the first application example that we'll look at, this was a graphite anode sample that had known contaminants that were stainless steel powders. So we analyzed this anode with a 1 millimeter by 1 millimeter elemental map with a 20 micron spot size that we did very quickly. It took about 2 minutes. And you can see how there is relatively high amounts of carbon shown in blue and bright blue. That's what we would expect on a graphite anode, which is mostly carbon. But what we identify on the chromium map is a couple of discrete areas with relatively high concentrations shown in those brighter blues. So what we did was, again, a secondary map with a smaller spot size and higher resolution. So in this case, about a 0.5 millimeter by 0.5 millimeter area with a 15 micron spot size. And we can very clearly see that there are 2 distinct particles with high chromium, high iron, high nickel that correspond to that expected chemistry of these 316L stainless steel powder particles that we knew were on this graphite anode. So this demonstrates the technique's ability to reliably measure the chemistry of contaminant particles. But what was unexpected in this study was this third particle that you can identify on the nickel map that does not have high chromium, doesn't have as high of iron. And so because of the advantage of the time of flight, where we're seeing all of the elements, whether we want to see them or knew to look for them or not, we can then take a look at those other elemental maps and see that we've got high lithium, manganese, and cobalt in that third particle that we've highlighted in red. And based on that chemistry, we determined this was actually an NMC cathode particle. So an unexpected contaminant particle was identified by this technique. And again, because you have the advantage of measuring the full chemistry down to the parts per million constituents, you can get a very detailed picture of what your material is that can be very helpful when you're trying to figure out, okay, yes, I know I have a contaminant here. I identified it with an optical technique, but what actually is this? Which tool did this come from? And that's where this technique adds a lot of value, is by giving you that full chemistry picture of that contaminant, helping you diagnose where it came from and prevent it from occurring in the future. So we'll now move on to our second application example, where we're looking at anodes at different charge states. So this is an example of kind of as you've developed a new silicon anode or a new battery chemistry, you're working on your cell geometry optimization, starting to increase the pilot line capabilities and process control. You can evaluate how your lithium is migrating between top and bottom of charge in these silicon anodes, and as well as potentially, optimize your formation cycling process as you're standing up this new cell geometry and chemistry. So what we did in this study was 3 anode samples, one of which was extracted at the top of charge, 2 of which were extracted at the bottom of charge. The only difference between these 2 bottom of charge samples is where they were taken from the cell. One was taken from the center of the cell, the other one was taken from the edge of the cell. And so you can see this diagram here of each of the 3 anode samples. We've got this 40 micron thick silicon anode that was deposited on a copper current collector. And the way that we analyzed these samples is with a 1 millimeter by 1 millimeter area. We used a 50 micron laser spot size, and we chose to overlap that spot as well. So we've talked about kind of the versatility on the mapping side of things, of being able to adjust the laser spot size to change the resolution of your map. On the depth profiling side of things, the user can change the laser power so that you're removing more or less material based on the power that is going into the ablation process. But then you can also choose to overlap spots, which allows you to just remove more material per layer. So that what we've done in this case is our objective was to try to profile through these 3 silicon anode cross-section samples and see how the lithium was distributed in each of these. So what we determined by doing this analysis is essentially we got 6 layers through the silicon, and then by the 7th and 8th layer, we were seeing that copper signal, which showed us that we had penetrated into the copper current collector. So now what we're going to look at is how is that lithium distributed across these different layers. And essentially, we just integrated the lithium, normalized it to the silicon, and compared that across the 3 samples for those different layers penetrating through the depth. So you can see on the top, that's that surface layer, and then each of those data points is the subsequent layers, where, again, we're looking at that average lithium to silicon signal with higher on the right. You can see the copper current collector occurring at about 40 microns, that 7th and 8th layer here. So first, I want to draw your attention to the blue data points and line here. So those data points were acquired on that top of charge anode. And we can see that overall, there's more lithium at the top of charge. That's what we would expect. Those lithium ions should be in the anode at the top of charge. And what we also see is there's a fairly consistent amount of lithium in those different layers. And so that is validating that, it seems that we have the right size of our electrode. We're getting a nice uniform distribution of our lithium ions at the top of charge. But then when we look at the bottom of charge anodes, there is still lithium in these bottom of charge anodes. So that suggests that we've got some amount of non-recoverable lithium tied up in the SEI. Potentially, on the surface, there may be some electrolyte decomposition that's occurring. But what distinctly was different about the 2 samples was once we got deeper into each of the samples, we see quite a bit of difference in how much lithium there is, even though they both started out kind of in the few surface layers in a very similar amount. So clearly we're getting some lithium accumulation that is different between those 2 samples, where again, the only difference between them is where they were pulled from the cell. So is this lithium accumulation potentially detrimental? Could this potentially turn into some lithium plating? All of this is very helpful to understand as you are developing an appropriate cell geometry and formation cycling process. Now, the final piece of the study that I want to show is what this actually looks like in 3 dimensions. So rather than just averaging and integrating across these different layers, let's take a look at each one of these voxels in 3 dimensions and see those different elements that were identified. And I want to point out that this visualization was done with Dragonfly 3D World that some of you may be familiar with. And so again, what we're looking at here is that top of charge anode where we see that copper current collector on the bottom. And specifically, we're most interested in how is that lithium distributed that we see in green. And we can see fairly uniformly distributed within that cross section. We see that there is a little bit of kind of surface heterogeneity on the copper current collector where we're seeing those lithium pockets. And then we did identify fluorine. So fluorine being a major constituent of the electrolyte, this may indicate that we're getting some SEI, solid electrolyte interface layer formation. And what was a surprise here is the trace amounts of cobalt that were identified. So you can see kind of these discrete areas of cobalt. And if this analysis had been done on the raw material, we could have determined, was this cobalt, an impurity that was in the silicon anode before it was turned into a slurry and distributed on the copper current collector? Or did this occur from a migration? Was this cobalt migrating from the cathode during the cycling process? So once again, I'll just let the video play once again so you can kind of see this full picture. Because again, a big advantage of this technique is being able to get that full mass spectrum at every single one of these voxels so that we can look at all of these different elements that tell us something a little bit different about what's going on in the cell. We see the lithium ions, we see the fluorine that indicates the SEI, and then we can see these trace contaminants that may be impurities or may have migrated. And talking about metal migration from cathode to anode is a great segue into our final application example here, which is how our technique was used to characterize SEI formation and a known amount of metal migration in a very promising battery chemistry, which is lithium metal anodes. So this is work that is done with our customer at SLAC or the SLAC National Accelerator Lab, the DOE lab that is on Stanford's campus, and specifically the group at SSRL, which stands for the Stanford Synchrotron Radiation Light Source. And for those of you who are familiar with this facility, you know that as part of the synchrotron, they have a ton of very powerful analytical techniques, most of which are X-ray based, that have a lot of powerful abilities on morphology and transition metal analysis. A lot of work has been done on this specific chemistry type on the transition metal migration. But what those techniques struggle with is reliably measuring lithium. And so that's where our LALI TOF-MS technique very well complements all of these capabilities at SSRL. So you can see this diagram on the right here, which was presented by our colleague, Eric Espinosa Villatoro, at an SSRL users meeting last year. And many of you may be familiar with this particular battery chemistry. The combination of lithium metal anode with a high nickel layered oxide cathode has a lot of promise. It can be have much greater energy density than some of the traditional lithium ion chemistries, but we also know that it's not quite commercial yet. And as we've mentioned, there are limitations with some of these conventional characterization techniques to fully understand the stability of the lithium metal anode and how these transition metal migration might be impacting the SEI layer, solid electrolyte interface layer. So what you're looking at on this slide is just a preview of a manuscript that is in preparation right now. You can see the title on the bottom of the slide here. And so I encourage you to keep an eye out for when this manuscript is published, because there's a lot more information that's included in this manuscript, especially including kind of how dopants have been explored in order to mitigate some of this transition metal migration. But the key point that I want to identify here is how LALI TOF-MS is helpful in identifying not only the metallic constituents that were also seen with some of the X-ray techniques, but also these SEI constituents. So what you're looking at here is two lithium metal anode samples, one of which had only undergone one cycle, the other of which had undergone 100 cycles. And when I play these videos, you'll see these different lithium species that our colleague Eric has interpreted as representing both the inorganic constituents, so mostly the oxide species, as well as some of the organic constituents of the SEI. So wherever you see lithium combining with hydrogen or carbon, for example, those represent the organic constituents of the SEI. So first I'm going to play the video from the one cycle sample. So you can see, this is mostly a lithium metal anode. We see that lithium combined with hydrogen populating in one area, the lithium combined with oxygen in another area. But overall, we don't see a super dense SEI formed quite yet after this one cycle. So again, noticing how the different constituents are distributed, as well as fluorine, which you see in pink, which was also identified here. I should also point out that these were more on the surface. These analyses were done with 5 layers on each of these samples. And now I'll play you the video of the 100 cycle sample. So this is the same analysis, the same 1.5 mm area done with 5 layers. But what we're identifying here is as we start to see these different species that are representing the SEI, we see a much denser SEI has formed after this 100 cycles has occurred. So we're seeing, once again, kind of a difference in where the inorganic versus the organic species are concentrating, but overall, a denser picture of SEI formation after this 100 cycle sample. And then eventually we see also where the nickel migration is concentrating as well. So again, not going to reveal all of the findings of this study. There's lots more information included in this paper, especially with some other samples that have dopants in them to try to mitigate this transition metal migration. But yeah, once again, just providing that picture of how this technique can complement the other analytical techniques and identify things that are not easily identified with those other techniques, and very impactful for SEI studies on these new promising battery chemistries. And I certainly want to leave some time for questions, so I will just quickly summarize once again, now that we've gone through those battery cell component examples, things on the anode side of things, how this technique helps R&D, process control, failure analysis. We saw the elemental mapping, we saw the depth profiling. One thing we've touched on, but I do want to specifically point out, is that those lithium metal anodes, because they are air sensitive, were analyzed in an air-free way, and that is a big advantage of this technique. Jeff talked about how the entire process is done under vacuum, and what we collaborated with our customers at Stanford on was an air-free transfer vessel that allowed them to actually load those lithium metal samples in a glove box environment, transfer it to our instrument, and then once it pumped down to a high vacuum, the vessel opened and we were able to analyze those samples in an air-free environment. So with that, I know we have a few minutes for questions, but if we don't get to your question, or if you want to talk more specifically about some of your specific materials and testing needs, please feel free to reach out to me by email. And thank you again for listening.
Perfect. Thank you, Ellen. Thank you, Jeff. Wonderful presentation. So those who have questions, we have a little bit of time for questions. So if you click on the bottom bar of your screen, there'll be a Q&A button. I can already see that we have some questions coming in. Please feel free to type in your question there, and we'll try to get to them in the remaining time that we have. Okay, so let's start on some of the Q&A. So we have our first question from Colin. Similar mass spec methods such as ICP-MS are subject to mass charge ratio aliasing between elements of interest in small organic ions. Are there any organic ions you've encountered in the battery samples that mimic the M-Q battery relevant metal ions such as nickel, manganese, or cobalt?
Yeah,
So
I'll go ahead. And, oh, go ahead.
I was just going to say that, yeah, I mean, this past example that we showed of, these different organic fragments that we saw, we certainly do see some organic fragments here, just by nature of how complex these battery samples are, even though we have optimized this to break everything down to the elemental level. So yes, we certainly see some organic fragments, but I'll let Jeff talk about like why we see fewer of those than traditional ICP mass spec techniques.
Yeah, it's a good question, and yeah, thanks for asking, Colin. So, like traditional ICP-MS, where you have generally an argon or a helium gas flow that's carrying, your particles through it, and there's also going to be trace amounts of, like you mentioned here, um, oxygen or carbon that's going to form in the plasma itself, and you're going to end up with a lot of interferences, right? And this is one of the challenges with ICP-MS is really having to dig into, what isotope should I use when, and am I going to run into an issue? And like Ellen just mentioned, we do still have some things that form either post ionization or during the process itself where they're not fully broken up. And that is where we can take that to our advantage in this case, and like what Eric did the work here for being able to break that out between what is the LIO telling me versus the Li2O versus the LIC, for example. But to your other point, do we see this in like the majors for nickel, manganese, cobalt? There's a couple of things there. One, um, these signals are generally much smaller, right? So whenever you do see a nickel, for example, coming up, you're going to have multiple isotopes that you are looking at in the mass spectrum, and you're not going to be flooded out by these organic compounds. These are generally more, when you're looking at more of a clean mass spec, you're able to see these organics, something in this case, right? But when Eric was looking at the nickel here, it was very clearly nickel because there wasn't enough interference. So hopefully that answers your question.
We have another question.
Mhm.
How does how does calibration for heterogeneous materials like ores look like? And can it be single element references, or does that require different concentrations of each element, same matrix?
Yeah,
Yeah, so I can share an application example of so this is like our ideal sort of like reference material, like what it looks like. I know, some other techniques will use like a single element reference for each element of interest. But for a solid sample technique like this, we're ideally looking for a reference material that has all of the elements quantified in kind of the same range that we're expecting for our unknown. So in this case, we're looking at two blended sediment reference materials that are quite similar in composition. And, they have the same kind of major constituents, minor constituents, and then trace constituents in parts per million level here you can see. And so, ideally, like we would have this matrix matched reference material that has all of these elements quantified, and then we're using that to quantify the other one. The example that I showed where we had multiple reference materials, that's what's needed when we don't have this nice scenario where we have, a true matrix matched reference material, and we can quantify all of the elements with a single reference material. I think the other piece that was being asked here is kind of like the heterogeneous nature of these materials. We know that rocks are very heterogeneous. In fact, this is a nice example of what was supposed to be, an ore powder reference material, supposed to have been homogenized, supposed to be, have gone through this rigorous process of defining it as a reference material. But, when we look at our elemental maps, we still see a lot of heterogeneity, and in particular, these sulfides in this ore powder. So, anytime we are trying to get a bulk composition of a heterogeneous material, making sure we're sampling a big enough area and getting a good representation of the bulk is part of our method development process. And because we are not digesting this entire sample in acid. We're not getting one number for these answers. And so, there's a lot of value in looking at these elemental maps and seeing the heterogeneity. But when it comes to, I just want to know my bulk composition, we'll typically do a relatively large area to make sure that we're getting a good representation of that heterogeneous material.
Yeah, and one last comment on that as well. We will be stay tuned for a new software package rolling out soon as well, where we're actually going to be having a model that will pull out, like in this example here, all of the, let's say, sulfides or molybdenum bearing sulfides in here, and treat those separately in space to be able to automatically apply different calibration curves to different mineralogies. We're really developing around that for the critical minerals market in general, and we'll also be rolling out a semi-quant method for that too. So stay tuned. It's exciting.
Thank you. And we have time for maybe one more question. On a related note, what is the camera resolution? I'm assuming that Molson uses voxel size to find features and areas of interest on the sample.
Yeah, so the micro camera. So as you saw, I think on the video, or maybe it didn't show it, but we actually have a micro camera that you can continually zoom into, and it'll transition to a live view of your sample. That's about a 600 or yeah 600 micron by 600 micron area that you're looking at about, and that's able to look at like the sub 5 micron feature range.
Perfect. We have a couple more questions, but I think we're out of time. We'll make sure to get to those questions and post. Ellen and Jeff has the information of those who've asked, and
Yeah,
they'd be happy
absolutely.
to follow up with what you guys have asked. And with that, that concludes our webinar program. Thank you so much, Ellen and Jeff, for that wonderful presentation. I think there's a very clear value proposition for TOF-LALI and you've demonstrated it both for the ore side and also for the battery side. And thank you, everybody, for attending today's talk. And we'll see you in the next webinar series.
Awesome. Thank you guys for
Thank you so
coming.
much, everyone.